Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Dr. Jennifer Heldmann, who's come across to us from NASA Ames Research Center, where she's in the Planetary Systems branch. Jennifer did her bachelor's in astrogeophysics at Colgate University, Central New York, and then did a master's in space studies at University of North Dakota. And then did her PhD in planetary sciences at the University of Colorado in Boulder. Following that, she then did a NRC postdoc at NASA Ames. And for a few years, she was a PI here at the SETI Institute. And then she moved across after that to the Planetary Systems branch. Her career is focused on research regarding Moon and Mars. And she was a co-I on the Alcross mission to look for water in the lunar polar regions. And she's also published extensively on recent water and gullies on Mars. She is also interested in finding terrestrial gully analogues and doing fieldwork in the Antarctic, the Arctic, the outback of Australia, the high Arctic of Canada, Atacama, and other places as well. She is also the PI of the Finesse, which is a survey science node, which is hosted at NASA Ames. That's where she's coordinating teams and doing field work in the Canadian high Arctic. And today we're going to hear about subsurface ice in Antarctica and relevance for Mars, and also for implications for habitability on Mars. So please join me in welcoming Jen.
Well, thanks everyone for coming here today, and for those that are watching on the web. And thank you, Adrian, for that very nice introduction. It's always nice to come over to the SETI Institute because I get to come and watch the talks, and now I get to pay it forward and give a talk. So hopefully we'll learn a few things about Mars and our own planet today. So I'd like to talk about Mars and periglacial morphology and ice stability. And I just want to set the stage for why I think that this is an important topic that we need to be addressing. Studies of ice on Mars are relevant to NASA, both in the science realm and in the realm of human exploration. And here's your one slide on NASA bureaucracy and the structure of NASA. Two of the directorates in NASA are SMD and HEOMD. SMD is the Science Mission Directorate, and HEOMD is the Human Exploration and Operations Mission Directorate. And so I think that by studying ice on Mars, I'll try to convince you that we can bridge the gap between SMD and HEO, science and human exploration, because we both care about the same things for slightly different reasons. So for science, why we care about ice on Mars, we have this guiding document from MEPAG, which is the Mars Exploration Program Analysis Group. And we are interested scientifically in the search for life on Mars, understanding Mars climate, and understanding Mars geology. And we can attack all of those through studying ice on Mars, as I'll show you. And then also for human exploration, looking down the road. MEPAG's goal 4 is prepare for human exploration. And there's also something called strategic knowledge gaps, SKGs, what we need to know before we send humans to Mars. And one of those is focused on water resources. So going with the mantra that exploration enables science and science enables exploration, I think by studying the ice on Mars, we can address both of these different directorates. So just in a little more detail, for life, why is ice on Mars today actually interesting? Well, we can characterize the present habitability and the search for extant life on Mars. Ice is a really good place if you want to protect biology, because any organic materials that are on the surface of Mars are going to be bombarded by radiation and be broken apart, and they won't survive probably long enough for us to go and find them. So you have to protect them and go down deeper. And so if you preserve something in ice, this is a great way to preserve these organic and biologic molecules. And it also, at the same time, can provide a source of water for the biologic activity, which, as far as we know, you need in order to have life. There's also climate. We're going to talk about climate changes over Mars during this talk. We can characterize Mars's present atmosphere, present climate, climate processes, and what happened in the past, because the climate is a big driver for what's going on with ice stability on Mars today and in the past, where it could have been and where it is today. And then geology. We're going to talk about some geomorphology, some surface features you can look at, which may or may not be indicative of what's happening in the subsurface, which are affected by the presence or absence of ice on Mars. So we'll look at a few of those as well. And then there's a human exploration in looking for these water resources. And something we need to do is assess the shallow water ice properties and occurrences as potential raw resources for ISRU, in situ resource utilization. And then that's for the ISRU portion, but also before we send humans to Mars, it would be nice to know if there was already extant life there for reasons of biohazards and also planetary protection issues. There are special regions on Mars where it's very difficult to explore because we don't want to forward or back contaminate. So for all of these reasons, I think studying ice-rich locations on Mars is a useful thing to do. So given that, here are sort of the 4 different topics I'll talk about today in the next 45 minutes or so. One is ice stability and depth to ground ice, so figuring out where is it and how do you find it. 2, polygon characteristics and the relation to ground ice. This is a surface manifestation of what's happening in the subsurface. 3 is geomorphology and ice type, so we'll look at some surface geomorphology and see if that can tell you anything about what's going on in the subsurface. Because remember, when we go to Mars, we have to be clever about figuring out where is the ice if we're going to access it for science and or human exploration. And then we'll do a little study in Mars landing site selection. So is there a good place, an optimal place where we might be able to go on Mars to address some of these issues with a future mission? So in order to look at all of these different topics, we're going to first start by looking at the Antarctic dry valleys. And this will focus on the Mars analog studies. Adrian mentioned I do a lot of analog work. So going to places on Earth that are somewhat like these other planetary environments. Since we're not sending people to Mars just yet, this is the next best thing, so we can do some in situ studies. And we focus on the Antarctic dry valleys as a Mars analog for a few different reasons. It's dry and it's cold, just like Mars. It's a desert environment, so especially as you go inland, away from the coast, you have very low levels of precipitation. And it's very cold. Again, especially as you go inland, you get average temperatures that are well below freezing. And I'll show you some data to support that as well. So because it's cold and dry, Antarctica is a very good Mars analog. We understand that it's not a pressure analog, right? We're still on Earth, so we're still at Earth's atmospheric pressure, whereas the Martian pressure is much less than that, about 1/100th of that. But we understand the limitations of the analog. And where we go is to McMurdo Station, which is outlined in red. That's the US base. And then we helicopter over to the dry valleys. And so I'm going to show you some of the work that I've done down there. Been fortunate enough to go down to Antarctica with some of our colleagues from SETI. Dale Anderson has led teams to the Antarctic and the Arctic for decades now. So as a longtime SETI PI, he's a very good person to go with. He knows just about everything about how to get there and a lot about the science as well. And Chris McKay was leading the group too, who also has done decades worth of polar exploration. So why we pick the Antarctic dry valleys in particular? So I've done work in the Arctic as well, also with Chris and Dale. And the Arctic is a very good Mars analog. It's very cold. It's a lot wetter, though, than Antarctica. And so on this little plot here where drier and colder are going on each of the different axes, you can see the Arctic is down sort of in the corner. It's pretty cold. It's not the coldest place. It's pretty dry. It's not the driest place. You get meltwater during the summer. You know, there's little puddles. You can work in a short sleeve environment in the summer. So it's cold, but it's not that cold. Then you move up to coastal Antarctica. You're getting a little bit colder and a little bit drier, and that's pretty good. But we really want to push ourselves up closer to the Mars case. So Mars today is way up in the upper corner. It's the coldest and it's the driest. And the next best thing that we've been able to find on Earth is this place called University Valley in Antarctica. It's in the upper dry valleys, and it's very, very cold and it's very, very dry. And just to show you where we're talking about, here's a map of University Valley, Antarctica. So this is in the dry valleys. Beacon Valley is the long valley running down the center. It's very famous. There's a lot of science that's gone on down there. And University Valley is this hanging valley that's just above Beacon Valley. It's about 300 meters higher, so that makes it that much colder. And you have dry permafrost and ice cemented ground in University Valley, which is just what we have on Mars, which is making this an even better type of place to go. And here's just a picture of University Valley looking down from the mouth of the valley, looking up. There's a permanent snowpack that's right there at the head of the valley. And then you can see there's the valley floor coming down. It's about 1.5 kilometers or so in length. So why are we so interested in this? What makes it such a good Mars analog? Well, there's something called dry permafrost. And we have it on Mars, and we have it in the dry valleys of Antarctica. So just so that we're all on the same page, permafrost is ground that stays below freezing. So it doesn't get above 0 degrees. And there are 2 types of permafrost. There's ice cemented permafrost. So you've got water that's frozen in between those grains of dirt. And there's dry permafrost, which has no water content in it. It's just dry soil that never gets above freezing. And then there's something called the active layer, which in the upper surface can seasonally warm above 0 degrees on occasion. So it makes sense that the top layers get the warmest because that's where the solar insolation is coming in. So if you look at these little schematics, we have ice-cemented permafrost, coastal Antarctica and in the Arctic, and you've got an active zone above that. That's great. The upper dry valleys, this is where we start getting into the brown areas, which is the dry permafrost, and that's the key. We want to have the dry permafrost as a Mars analog. You don't have that in the Arctic, so that's a limitation of the Arctic analog. And you can see this is unique to the high elevation dry valleys, where we've got an active layer. So I'll show you some data showing, yeah, you can warm up the active layer. The interesting thing about the active layer, though, is that when there's dry permafrost, there's no liquid there. So it's very hard to melt something if there's no water there to melt. So you have dry permafrost, and that can be underlain by either ice-cemented permafrost, massive ice, or nothing at all, depending on how far down you dig. So dry permafrost is the key, and it's key because we see that we have it on Mars. It's a very unique situation that we're in. It's because here's an image from the Phoenix lander, which landed in the Martian Arctic, and that's the scoop that scooped away that dry permafrost over the top. And just down below the surface, you can see the white. That's where you have ice. So we have the same situation in the dry valleys. And in the high elevation dry valleys, these are the best Mars analogs for this type of work because they're the only places on Earth where we have ice-cemented ground beneath the dry permafrost. So that's what's driving us really to go all the way to Antarctica to do this type of work. So let's talk about melting and past climate on Mars. So we know we sent Phoenix and we dug down and we see that there's ice there. There's a lot of other evidence for the ice as well. So that's great that it's frozen now. But we believe that it could have had the opportunity to melt as recently as about 5 million years ago. Right now, we're in a period of low obliquity. So you can see time is on the x-axis there. So 0 is present day. And so we're in this low obliquity period. But about 5 million years ago, the tilt of Mars was higher. And that's that obliquity transition where you have a higher tilt. And so what that means is you're getting more insolation towards the polar regions. So at high latitudes, you're getting more and more direct insolation, which gives you higher temperatures, which can lead you to temperatures that would allow that ice to melt. And so it's believed that since we know that there's near-surface ice there, we could have had possible melting in the relatively recent past. You know, in geologic time, 5 million years isn't that long ago. So you've got the presence of the ice. You've got a low elevation because you're up in the northern plains. So you're above that 6.1 millibar triple point threshold for the stability of water. And you could have summer temperatures that could have been higher than 0 degrees C. So it's been argued by many people that the Martian Arctic may be one of the most recently habitable places on Mars. So this might be a good place where we want to go and do some astrobiology type work. Okay, so let's go back to our University Valley analog, since we can go there and we can actually collect data. So what we've done is tried to characterize the ice, and we're trying to understand its presence and its distribution, and trying to understand its stability as well. So what we did is we said, okay, well, let's measure the thickness of that dry permafrost layer. Basically, how far down do you have to go until you hit that ice table, until you hit that ice-cemented ground? And so we went out with, you know, sticks and shovels and dug pits and made a lot of measurements, and that's what those colored dots are. Those are the measurements of the depth down to that ice-cemented ground. And it's very interesting that there's a somewhat linear relationship from distance from the top of the valley down the length of the valley and the depth to ground ice. So essentially, remember I showed you that picture of that snowpack that's at the head of the valley? As you go further and further away from that snowpack down the valley, your ice gets deeper and deeper and deeper. And that's very interesting because this gives us a very nice natural analog to do a lot of ice stability and geomorphology studies. So we tried to characterize this environment as best we could. We put out a MET station. This is Margarita Marinova. She was deploying those instruments with the standard MET station suite of sensors, temperature, relative humidity, radiation, et cetera. And then we also instrumented several ground ice sites at a shallow ground ice, a medium, and a deep site. And we put a slew of instrumentation underground. As you can see there, I'm deploying some of those instruments to measure things like temperature and relative humidity throughout the column of dry permafrost and into that ground ice. So we could try and understand what was happening over the course of several years. So I'll show you some of that data that we're putting together to publish now. So this is the solar radiation So this is good verification that our instrument was working, because you can see that the solar radiation goes up in the summer and is 0 in the winter. And that's just how it should be, because you don't have any sunlight in the winter months down in these locations in the Antarctic. So it's sunny all day. We have average summer solar noon values of about 475 watts per meter squared. Compare that to the 500 to 600 for Mars. And so you're relatively in the right regime. So we know which days were sunny, which days were cloudy, and how much radiation is coming in, which is good for doing energy balance models. We also have some air temperature data. So I've drawn a line here at the 0 degree C mark, so you can see where the freezing mark is, basically. And you can see that the air temperature doesn't go above 0 degrees C. So it's cold. I told you it was cold, and so now I'm just proving it. And it makes sense that in the summer, the temperatures go higher. In the winter, the temperatures go lower, getting down to about minus 45 degrees C, with an annual average of minus 22 C, which is pretty good for Mars, talking, well below the 0 mark. Here's surface temperature. So right at the top of that dry permafrost layer, you can see, looking at where the 0 line is, that some days in the summer, the surface does get above 0. So that's what we were talking about, is that dry permafrost layer right at the surface can actually get above the 0 mark, even though your air temperatures are still below 0, just from that heating. Remember, we're talking about the dry permafrost at the surface, though, so we're not getting any melt in this location because there's no ice there to melt. Here's within the dry permafrost itself, so not at the surface, but down a little bit. And again, you can get above that 0 mark a few days in the summer, but we're still not melting anything because we're still in the dry permafrost. And it's still really cold for most of the year, down to minus 44 or so. We also put some relative humidity sensors in there to see what's going on with the RH. And so I just drew a line at about the 95 mark. That, with our sensors, basically means that it's saturated. And so it's interesting, in the summer, it's lower, and in the winter, it's higher. And this is because in the summer, we don't have much surface frost or surface snow cover, so things are pretty dry. And then in the winter, you get some snow coming in, blowing in over the polar plateau, and getting deposited on the surface there. So you actually do get some surface frost cover. And that has a big effect on the stability of the ice. And we're writing a paper about that right now. So just to see that there are changes in the surface frost and ice cover as a function of season. And you can correlate that with temperature as well. So when the temperatures go down, when you're in the depths of the winter, the RH goes up, because this is when you're actually getting some of that snow and whatnot able to stay on the surface. And what's going on at the ground ice temperature? So remember, we have this layer of dry permafrost, and then we have this ice table. So what's happening right at that ice table? Well, what's happening is it's staying really cold, which is very Mars-like as well. We're not getting anywhere near 0 degrees C. So now where we have ice, we don't have temperatures high enough to melt that ice. So it's very Mars-like in this respect, that we never get the temperatures that we need to melt the ice. So we're in a vapor-dominated regime where we don't have liquid water melt. So any movement is going to be very slow and through vapor. And then we put sensors inside the ground ice as well. You can probably guess that if you're not melting at the ice table, if you go deeper, you're probably not going to melt there either. And that's the case. It just stays consistently cold and very, very low temperatures throughout the course of the year. And we've got 3 years worth of data just that I'm showing here. So we believe that. So to characterize University Valley and why this is such a good Mars analog, we have the dry permafrost overlying the ice-cemented ground, which is unique to Mars and the dry valleys on Earth. So that's why we go there. In University Valley, we see this trend with the increasing ice table depth going down as a distance from that permanent snowpack. So as we go down the length of the valley, the ice gets deeper. And we're going to use that to learn about stability and geomorphology. Looking at the data, the air temperatures never get above freezing, and that's consistent with what we would expect. Air temperature is driving the surface and the subsurface temperature, so we can see that in the data. There's a damping of that temperature wave as you go down with depth. And remember, it's only that top surface layer in the dry permafrost where you can get above freezing. Surface and dry permafrost can get above freezing, but there's no melt because there's nothing there to melt. And the ground ice never gets above freezing, so you're not getting any melt there either. And that's what's putting us, as I mentioned, in this vapor phase transport on Earth. And that's what's happening on Mars today, too, because we're not really getting a lot of melt water that's circulating. It's all vapor transport and vapor deposition to create that ice. And temperature related with relative humidity. We're seeing that, as we expected, you're getting some of that snow deposit during the winter months when it's cold and dark. Okay, so we know now that University Valley is underlain with this ice table that changes with depth. And if we look at the surface of University Valley, you can see that the bottom of the valley floor is covered in polygons. That's what you're seeing. Those are basically troughs that are outlined by the snow. The snow preferentially likes to sit in the low spots. So I like this image because it actually shows you the polygons, and they span the whole length of the valley floor. And we know from periglacial studies that polygons are indicative of subsurface ice. So just to keep everybody on the same page, what are these polygons that we're going to talk about? Polygonal pattern ground forms, seasonal thermal contraction cracking, and permanently ice-cemented ground. So you've got to have the ice underneath, and then these cracks manifest themselves on the surface. You can see there's our tents for scale. So there's our camp. And so I'm going to show you some of the sizes of these polygons. You can see them from remote sensing. You can see them from the ground. And so what we noticed when we were out there is that the size of the polygons changes in different places in the valley. And it's in a predictable pattern because they change as a function of distance down the length of the valley, which should sound familiar because something else changes as a function of distance down the length of the valley. So when you're at the head of the valley, that's the lower picture, near the snowfield, your polygons are relatively small. And then as you go away from that snowfield and further down the valley, they get bigger, and they're biggest at the mouth of the valley. So what we did is we took some aerial photography and we actually measured these and quantified how big is big. And that's what this lower plot is, showing the diameter of the polygons as a function of distance from that snowfield. And they tend to get larger the further down you go. And then we binned our ice table depth measurements to say, okay, well, what's the ice table doing at these places? And the ice table is getting deeper and deeper. So there seems to be a correlation with deeper ice means bigger polygons. So to explore this a little more, we collaborated with Mike Mellon at the University of Colorado, who has for several decades now been doing modeling of ice regimes, thermal stresses, polygons, et cetera, because we wanted to see if the size of the polygons made sense and could be predicted to match with what would be expected given the ice table depths that we're seeing. So basically what you do is you make a plot. This is up in here. This is part of an output from Mike's model, and showing when your peak stress, in that ground exceeds the strength of that ground, you can determine what that corresponding ice table depth can be, or will be. So if you look at the plot over in the upper right, you've got ice table and polygon diameter. So you would expect that the deeper you go, the bigger the polygons will be. And so we thought, okay, the general trend works, and what if we overlay our data on top of that? Do we see the same type of thing? And so that's the lower plot where the colored symbols are showing our data, ice table depth and polygon diameter. And for the most part, they follow the predicted curve where you have deeper ice giving you bigger polygons. There was one exception to this general trend, and I've circled that and just called it the baby polygon site. Because when we plotted these up, Mike said, what's going on with these? This looks pretty good except for this little cluster of plots down here. Why aren't those following the curve? And I said, oh yeah, I remember that place. It was in the middle, sort of towards the middle of the valley. And it was like maybe a deflation hollow or some type of newer surface where we had smaller polygons that weren't as well formed, and they looked like they were babies. They were baby polygons. So I think there was something different that was happening in that particular region, which is why it was different from a morphology perspective and just kind of stood out. But in general, the trend holds that the deeper the ice, the bigger your polygons are. So we can continue to use that to try and understand, okay, well, how long did it take to form these polygons? How long was that ice there in order for those polygons to actually form? And if you look at the morphology of the polygons itself, these, as polygons go, are pretty mature. They're pretty well developed. They have well-developed troughs. You can see the troughs very clearly. Whether they're filled in with snow or you're just walking over them, it's pretty obvious. Most of the junctions, if you actually look at them from a statistical standpoint, are equiangular, which is what mature polygons tend to do. And they have a consistent size within regions. So the small ones are clustered here, the medium ones are here, the big ones are down here. You don't really have them mixed up. It's pretty well segregated. And so what this is telling us is that there must have been some stable conditions over time for these polygons to actually form. And the present day ice table depth must represent an ice table depth over at least the time scale of the polygon development. So the ice table must have been relatively stable, at least as long as these polygons developed, because they had to have had time to get to their mature state that they're at now. I'll show you a case on Mars where that's not true, but for University Valley, that seems to be the case. So if you look in the literature, you can see what the understood progression of polygon development and ages are. When they start, they're kind of irregular, kind of 90-degree angles in these sort of arrays. And then over 10 to the third to 10 to the fourth years, you start getting a regular size distribution. Things start to equilibrate. You get these equiangular triple junctions that we're seeing. And then by 10 to the fourth to 10 to the sixth years, you're getting these mature polygons. This is more along the lines of what we're seeing, 5 to 6-sided, et cetera, et cetera. So we conclude from this that the University Valley polygons are probably at least 10 to the 4 years old, based on their morphology and our understanding of the ice table depth and how those polygons would form. So now we can start to put some ages on these surfaces and the length scale of the ice having been present. We can try and use the same logic to look at Mars as well, because that's really what we're trying to do here, is use Antarctica. It's interesting to understand Antarctica as its own entity. It's also interesting to use it to understand Mars. And so, for example, if we look at the Phoenix landing site, where the Phoenix spacecraft landed, we see multiple sizes of polygons in this place. You can see they're small-scale polygons, so on the order of 3 to 6 meters or so. There's medium-sized polygons, and there's big polygons with rubble piles. And they're all mixed up. They're all jumbled. They're not as separated like they are in University Valley. So there were probably multiple episodes of polygon formation and cryoturbation happening under varying ice table depths. So at least this location on Mars probably did not have the same stable type of climate environment that we had on University Valley, because we're seeing this jumbled mix-up of these different sizes of polygons. Okay, so what can we take away from this part of it? Ice table depth is a major factor controlling the polygon size. And as we mentioned, deeper ice is larger polygons. And the dry permafrost is a nice thermal blanket to isolate the ice table from wide temperature swings. So we can see that it's like this nice insulating layer that helps to keep things stable. And the ice table in University Valley was probably relatively stable for at least 10,000 years. And that's based on the morphology and the maturity of the polygons. You don't have these irregular polygon patterns and troughs and rectilinear arrays and that sort of thing. In contrast, the ice table in the Martian Arctic has likely changed over polygon formation timescales because we have the superposition of these different sizes of polygons. So things have been changing more on Mars than they had been in University Valley over the length scale or timescales for polygon formation. So what we'd like to do is try and understand a little bit more about what's happening at the surface compared to what's happening in the subsurface. Because we have this issue on Mars where it's not exactly easy to send a spacecraft to Mars, and we haven't actually sent people to Mars. So we need to do all we can using remote sensing and whatnot to try and understand the subsurface ice. So we're going to look at surface geomorphology. And we see some similar geomorphologies in the Martian Arctic and in the dry valleys of Antarctica. Not just University Valley, but also down in Beacon Valley. And so here's a picture of Beacon Valley. So this is a little different than University. You've got this dry ablation till above, and then there's massive ice down there. It's like ice cubes. It's just pure ice, which is very different from University Valley, which is ice cemented ground, so dirt and soil mixed together. So it's been in the literature that there are certain features that you see in the dry valleys that you also see on Mars, like cracked rocks. Here's a cracked rock on Earth and a cracked rock on Mars. Pitted rocks, rocks with little holes and divots in them. Perched rocks, rocks that are different from the host rock that are sitting on top of those rocks. And then polygonal ground, which we've already talked about. So the first 3 categories of features that are the same on both Mars and Earth are basically, I would tell you, rock weathering and erosion. That's how they formed. Whereas the polygons are thermal contraction and really indicative of what's happening in the subsurface. So this is just a lesson on comparative geomorphology and understanding the processes that are forming the features that you're seeing to understand the implications for the formation. So for example, the rock weathering and erosion, you have cracked and shattered rocks. That's mostly just rocks that are physically broken apart. There's a lot of processes that can do that: chemical weathering, hydration, insulation, et cetera. You can crack your rocks, all happening at the surface. Pitted rocks, same thing. Mostly salt weathering, or again, physical weathering, aeolian abrasion, winds hitting other particles onto it and making pits and whatnot, not really related to what's happening in the subsurface. And the same thing for the perched cobbles and the pebbles. They can be saltation events that are basically the wind blowing pieces of rock on top of other pieces of rock. They can be left behind from glaciation, depositing rocks as that glacier retreats back. Not really indicative of what's happening in the subsurface. The only thing that really is the polygonal ground, which is why we focused on it for most of this talk, because that is a surface manifestation of the subsurface ice conditions. So I think you have to be careful in that sometimes geomorphology is not uniquely related to the nature of what's happening in the subsurface. For example, you can't use those, the rock features to tell you if you have ice-cemented ground or massive ice, because there's no way to tell the difference. And we see both in University Valley and Beacon Valley, which have two radically different ice regimes in the subsurface. Maybe if you have a fine-grain ablation till, that's one way to tell the difference, but you can't really tell that from remote sensing. So how are you going to tell if you've got subsurface ice in the form of massive ice or in the form of ice-cemented ground? Well, I would say that you have to get in there and drill it. You have to actually access it and get some in situ measurements to figure that out. So if we were to go ahead and say, okay, we need to drill into the ice, that's a big endeavor. And going back to basically the first slide where we talked about the importance to both science and to human exploration, you're not supposed to read this chart. All this is showing you is that there are a lot of science goals on the, I guess, the y-axis in this case, scientific objectives for looking at Mars science questions. There are also a lot of SKGs, strategic knowledge gaps, for filling in holes of what we need to know before we send humans. And where there are colored boxes in there, this is from one of our MEPAG reports, is where there's overlap, where you can make the same measurement and you can address both the science and the human exploration goal. So there are a lot of ways in which you can actually address these issues of life, climate, geology, prepare for human exploration by doing these types of studies. So I'm trying to make the argument that by doing these types of missions, you can address both science and human exploration. And so I'll talk to you about one concept that's been worked on over at Ames for quite a while, the Mars Icebreaker mission concept. And there are some nice papers published in astrobiology and other journals that you can go and, if you want to read more detail, I'll just give you the high-level points here. But the primary motivation is searching for evidence of life on Mars. And as we talked about in the beginning, a good place to do that is to go and search in the ice. Preservation potential, water source, recent habitability, et cetera, et cetera. So the science goals of a mission type like this, search for biomolecules that would be conclusive evidence of life, search for organic materials in the ground ice, determine the processes of ground ice formation and the role of liquid water, understand the mechanical properties of that ice-cemented ground, and assess recent habitability. And so how you would do that? Well, you need to drill, because you need to get down into the ice and get some samples of that ice. You need to handle those samples, and then you need a suite of instruments to actually answer those science questions. So there's a whole science traceability matrix to address that. And how do you get to Mars? I don't care. I'll take any ride. I'm not picky. There's a picture of the Lockheed Martin Phoenix lander. It's landed on Mars. We know it can do it. Put the icebreaker payload on that. There are other entities that want to go to Mars. So here's a picture of the SpaceX Red Dragon with visions of landing on Mars. We'll put the payload in that. I'll take any ride. I have no shame. So if we were to go and send one of these missions to drill into Mars ice to answer all of these interesting science and human exploration questions, where would you go? Is there a good place you could actually do this? And so when we're looking at subsurface ice, there are two places on Mars where we have direct observations of ice. One we've already talked about is the Phoenix landing site. Landed up in the Martian Arctic, pretty high latitude. We scrape down. There's that picture again where you can actually see the ice. However, if you're trying to mesh science and human exploration, this may not be the best place to go because it is at high latitude, which means it's really cold and it gets covered in CO2 ice every year. So maybe not the best place to put a human base. Another place for mid-latitude ice is near the Viking Lander 2 site. Viking itself did not touch the ice, but there's been some science done since then, discoveries since then, saying, you know what, it was probably really, really close. And I'm going to step through the evidence for that ice. So Viking is at a more mid-latitude location. So it's lower latitude compared to Phoenix, which is a bit more amenable to sending humans there. Closer to the equator would probably be better. And so we're going to step through some of the evidence for ice at this lower latitude, looking at surface morphology, excavated craters, gamma ray data, and some numerical modeling. So remember, we've harped on this. If you see polygons, it probably means there's ice below it, right? We got that message. So you look at the images near the VL2 site, the Viking Lander 2 site, and they're covered in polygons. This is one of the reasons Viking went there. a lot of evidence for widespread subsurface ice in this region. You can spend hours, days, months looking at high-rise imagery and looking at beautiful polygons all over these terrains. And we've done that, I'll show you. There's also a really nice paper that came out in '09, and there's been some follow-up work since then by Byrne et al., looking at excavated icy craters. So this is pretty cool because you've got before and after pictures of places on Mars near these latitudes, near the VL2 site, where a new crater has formed, and we've actually been able to see the after effects. And these are high-rise images, so high-resolution images, false color data. And where you see the white, that's actually ice that's been excavated in the subsurface. So we have this very nice natural experiment that's been going on, saying, hey, if we punch the surface and look down, you know, not too deep, I'll show you how deep in a minute, there's ice there. And we see it in the high-rise. Here's a CRISM spectra showing that you're seeing the water band, so it is water ice that you're actually seeing. The ice fades over time. So here you can see you've got ice in these two little spaces, and then it fades. This is just the fading curve over here because the ice is going away. It's going to sublimate because it's not stable in the Martian atmosphere right now. So you can see the disappearance of that icy material. And here's a map showing there's these 5 different sites that were published in this paper. Here's VL2 over here towards the left-hand side in Utopia, right down there. And then there's 5 other sites in this very interesting region. And the depth of these impact craters is from, you know, a little less than half a meter to like 2.5 meters. So you're not talking very deep where you've got ice. And according to the modeling, Viking probably just missed the ice when it was going down, you know, by not very many centimeters. So close. But the takeaway message is that there's ice in the relatively near surface in this particular region. So we decided that we wanted to look at this in a little more depth and see if there are some good spots in there to explore. This is also corroborated by the gamma ray spectrometer data. So this is basically maps of hydrogen, from which you can infer where there's ice, showing that you've got subsurface ice, particularly up, you know, where Phoenix landed, so up there in the white. And then there are pockets over near, here's the Viking site over here, over there on the far right for you, the VL2 site. So from the gamma ray data, we expect that there would be subsurface ice. So again, this is consistent with what we're seeing with HiRISE and with CRISM and now with GRS, and also numerical modeling that had come out even before those discoveries by Mellon et al. In a series of papers predicting the geographic location and the depth of near-surface ground ice, because it's vapor-deposited ice that's coming in and forming these deposits. And the modeling agrees quite well with the GRS data. So it seems like we have a pretty good handle on, you know, where the ice is and where that boundary is. So what we did is we decided to do a landing site study to see if there are any places in this region of interest identified by Byrne et al. From those icy craters where we can see that there's ice. And is there a spot where you would land an icebreaker type mission where you could actually drill down and access the ice? We've landed the VL2 site before, so in theory we know we can do it. But as I'll show you, maybe there's even a better spot. VL2 was really rocky, and that makes a lot of engineers nervous even today. So, as I mentioned, we know that we landed at VL2. We're going to use that as our baseline because we have images from orbit and we have images from the ground. So we have a pretty good handle on how to tie the two together at the VL2 site. Here's a picture of the Viking landing site. You can see it's really rocky. And engineers are still worried about this. And I was not in this career when Viking landed, but I've read a lot of papers and talked to people about it. And many have said that they probably wouldn't have landed there if they knew it looked like that when they got down on the surface. So now we kind of know too much. So is there a better spot in this region where we would feel more comfortable landing? So what are our landing site criteria? Well, we're going after the ice, so you got to have ice there. So we want to be in this region of interest where we have all this evidence for ice, polygons being one of them. And we want to avoid a lot of the landing site hazards, rough topography. We want to avoid a lot of rocks. We want to avoid a lot of boulders, and preferably don't land, you know, on the side of a big crater. Engineers like nice, smooth, flat, boring areas. Fine. So we just developed a ranking scheme for going through each of these criteria. I won't, you know, dwell on this too much, but basically, do you have polygons? Yes or no, or sort of. Polygon definition, you know, how evolved and mature are those polygons? Do you have rough topography? Over here, it's not rough, it's pretty smooth, or do you have big cracks and big surface features that you have to worry about? Rock density, so a rock density of 3 down here is the VL2 site. It's pretty rocky. There are rockier areas. There's a very dense site. But there are also areas that are a lot smoother with fewer rocks. Also the presence of boulders. Some areas are pretty free of boulders. Some have a few, and some are pretty well covered. There's a lot of boulders near the edges of craters and craters themselves. You want to avoid large craters, and there's also a smattering of smaller craters as well. Again, just getting into the landing site safety. So what we did is we took all of the data that we could pull from this region of interest. Here, this is just showing, reminding you where the Viking Lander 2 site is, and then where all those other sites for those icy craters are. And we just went through and we made maps, basically stoplight maps. Red is for this criteria is no-go, don't land there. Yellow, marginal. Green, looks great. And so we did that for each of our different landing site criterion. So here is the presence of polygons. You can see there's a lot of polygons near VL2 over here. There's a lot of polygons down near Site 5 in the other corner. And then a kind of a smattering throughout the rest of the region. Topography is decent around VL2. There's not a lot of large hazards to avoid. A smattering sort of in the middle part and around by 5 is pretty decent. Boulders, not too many near VL2, a lot in this middle region. And then when you get back over to Site 5 around 190 longitude, you're doing okay again. Rocks, pretty randomly distributed. You can see that near VL2, it's actually pretty rocky compared to the rest of the region. Polygon definition, how well defined are your polygons? How mature are they? Presence of big craters, you've got a few big craters in the middle plains there, but the rest is pretty okay. There's a pretty random distribution of small craters, which you might expect. Cratering should be pretty random. And so to make a long story short, you can go read the infinite details in our astrobiology paper if you really want to. It turns out that one of the Bernadal sites, Site 5, fits all the criteria. And we didn't know going into this if any of those sites would or any of the other areas in that whole region would actually give us all greens across the board, basically. But it turns out that Site 5 did, which was really quite nice because now you can say you can land right near this crater where you saw that there was ice. So if there was ice in that crater, it's going to be a little bit more widespread. You don't have to land in the crater, but somewhere nearby. You've got polygons, not a lot of rocks, not much topography, not a lot of craters and landing site hazards. So I would argue that if you wanted to go and do an icebreaker type mission and drill into the ice for all of the interesting science and human exploration reasons we've talked about, there is a place that you could go in the mid-latitudes where we have very good evidence that there actually is ice there to access and that actually would be a safe landing spot for you to actually set down your spacecraft, whichever spacecraft that may be. So just to summarize what we've talked about and then we can discuss, I think that high priority science can be accomplished through the study of Martian ground ice. So we talked about why this is important for life, habitability, biomolecules, organics, ice formation, stability, etc. I think you can also, at the same place, prepare for human exploration at a site of known ice occurrence. And this, again, is important for life, for biohazards, soil toxicity, characterizing that water for ISRU, landing site certification, send a robotic precursor first before you send your human assets down. And there's a viable landing site within the VL2 region, which has fewer landing hazards than the actual VL2 site and observed near-surface ice. So I think it can be done. And with that, I'll wrap up and take questions.
If you have any questions for Dr. Heldmann, put your hand up and I'll ask the first one. So with regards to the University Valley and the polygons there and the ice, subsurface ice, do we have any ideas on habitability of that ice and like bulk organic contents or anything like that?
Yes, actually there's a corollary project going on with our team that went down to University Valley. And the biology aspect is being run out of Canada, actually. And so they went down and they did their sampling because this was it's still going to be a PhD thesis. You know, what is the habitability of the subsurface in University Valley? And the short answer is they can't get anything out. There's just, you would expect there to at least be, you know, on the walls of the valley, there are microbes that are living in the rocks that are falling in. You at least expect to see those. And like the subsurface samples, like they are having a very difficult time extracting anything. So it's very, very barren, which was surprising and not really what we expected. The short answer is there is a whole biology component that's being done. That would be a good SETI seminar series talk. And it's been very challenging and surprising.
You volunteering to give that talk?
No, I'm offering up our colleagues.
That was interesting. Can you give me a little more background on the term periglacial? Does it really have the same meaning on Earth as in Mars? Is it equivalent to permafrost? Or is there some stronger message there in that word?
I can only speak from my own mind. I don't know what I should probably look in the actual dictionary of, terminology. But I just, for myself, assume that this means ice-related, because all of this, this whole realm of study in this particular talk is talking about the subsurface ice, irrespective of what type of ice it is. So, and I should probably make the distinction much more clear between ice-cemented ground, which is, you have ice filling the pore spaces. And on Mars and in University Valley, it's probably coming from the top down. And that's why you're in the vapor transport regime. It's not meltwater that's percolating in so much. It's just vapor being deposited, and that's what happened on Mars. University Valley is a very different story because that's massive ice. I still term that periglacial, but it may or may not be accurate. And that's where you have the massive ice, also underlain by the dry permafrost layer, but that is just solid ice. So there were no, on my part, no implicit or explicit connotations with that.
Yeah, thank you for the talk. And I have a question for you. Do you know why they couldn't find any or isolated anything from the University Valley? There is any explanation for that?
I think there's not much living there. I mean, and we're trying to mesh that now with the temperature data. I mean, it's super, super cold. And even in, even in the dry permafrost layer, you're mostly well below, tens of degrees below freezing the whole time. And there's no liquid water content. So there's not much for them to live on. I mean, yeah.
If you were to optimize your landing site, instead of for the combination of the human and the science, but for each one individually, where would you go for those two?
Well, Phoenix is a really good spot to do Mars science. And so there's a lot of reasons to go back to the Phoenix landing site because we literally just scratched the surface. And so, I mean, Phoenix was picked out of SMD for a reason, for purely science purposes, and you can get your mission done. You know that there's ice there. You know that it's right here in the upper few meters, and you don't have to last over the Martian winter. So that's a perfectly fine spot for doing it. For the human case, talking with all of the folks that are putting together the human mission architectures, both in NASA and outside of NASA, they just really want to be closer to the equator because then you get more solar insolation, you get more benign temperatures, you can get more energy. And it's a trade-off that hasn't been solved yet because they want to be closer to the equator for insolation, but they want subsurface ice. And I'm like, well, you can't have both. And so trying to convince them where the sweet spot is, and it looks like the sweet spot may be in this VL2 site because you start going further down, and now your temperatures are getting higher, which precludes you from having ice in the near surface. So where that sweet spot is still TBD. So I think, yeah, it's a good question because there's different answers for both.
How do they know what the Mars obliquity has been doing for the last 5 million years?
Yeah, there's a lot of modeling that's been done. Lascar has a series of papers on that particular topic, and it's basically grounded in modeling of what the obliquity has been, the past Martian obliquity. And it tends to match pretty well with, from relatively recent geology and geomorphology of what we see and what we understand Mars was doing. So that's the short answer.
The hydrogen map, the GRS data, that's picking up water of hydration as well as ice. Have you distinguished between those
Yes.
in your analysis?
That's a good point because, okay, 2 points on that. For the GRS data, the footprints are huge. They're like 300-kilometer footprints. So we have to be careful when we look at GRS data that you're really looking at a very wide area, much bigger than what we're talking about for these landing sites. And right, it picks up the hydration as well. So that's another conversation that I've had many times with the human exploration folks because it's dangerous to send them that map because they say, look, right at the equator, there's this big, block of hydrogen. And like, it's not ice. It's, it's hydrated minerals and other things. Why can't we just go there? Like, it's not ice. So if there are any GRS people, what we really need is not that we know the actual answer, but a way to distinguish between where the ice is and where it's hydrated materials, because it can be very misleading. Yeah, they can go, yeah, and there's probably a mix higher up too. So, and yeah, that's why the story gets so complicated, and engineers don't like complicated.
Okay.
They want yes or no.
Permafrost on both Antarctica and on Mars has to have a bottom. As heat comes out of the interior, there has to be a point where it's melted on the bottom. So any ideas how deep that could be in either place?
That is a really good question. We've tried to address that. So in the Antarctica case, we don't know. And we've wanted to take some cores and take some deep cores. Even just coring through that snowpack is very challenging. So I don't know how deep it goes. It's easier for me to put limits on how deep it is from the surface, obviously, because we can go down like at the mouth of the valley, and we've dug pits, you know, like a meter deep and haven't hit the ice table. So like, all right, it's either not there or it's deeper than that. But the bottom part is really hard. For the Mars case, there's been some modeling that's been done, and there's been some research that's been done. Clifford et al. Have done, I mean, he's done almost his whole career on trying to model the Martian hydrologic cycle and seeing how deep it goes, probably on the order of, you know, kilometers deep, but we don't really know. And we have some subsurface data and ideas on the ice, particularly in the polar regions from like the radar data, but I don't think that we know enough to say how deep it is, but that's a very good question.
I have a follow-up. I thought.
Sorry?
Anywhere on Earth with biology below the permafrost, probably Siberia.
Oh yeah, you can go down in like, I mean, there's groups doing work down in caves and like super deep subsurface, and they're finding things growing there too, yeah.
Perhaps naively, I assumed you would calculate that depth if you knew the heat flow.
If you knew the heat flow.
Have you not measured heat flow in the Antarctic?
Oh, for the Antarctic.
Yeah.
Personally, I haven't. I'm sure someone has.
Yeah.
But the complication with that, especially like I've published on this for Mars too, and so the thermal conductivity of those layers, whether it's the overburden layer and then also as your ice content changes, the value for the thermal conductivity changes over orders of magnitude, which therefore changes your isotherm depths. So I've got ranges, but I'm hard pressed to actually pin it down. And that goes for even doing, you know, hundreds of meters down to see where the liquid water would be, because how far down do you have to go until you get warm enough that you have liquid water? Depending on the thermal conductivity you use, you can go down, you know, 100 meters, or you can go down 5 kilometers. So I would say there's ranges, and there's been some work done, like Mike Mellon has been taking samples, and he's developing a new lab to do measurements of thermal conductivity on the Martian material, or the Antarctic materials, to try and put constraints on that, because I think that's the biggest unknown.
Well, if you have any more questions for Jen, I encourage you to come up and ask them just as soon as she's finished here. And Jen, I know that you've wanted one of these for a long time. This is a special SETI Talks mug.
Thank you very much.
There's a couple of robots there that were talking about periglacial processes on Mars, I'm sure.
As they should.
Yes. Please join me in
Thank
thanking Jen
you.
for a great talk.